Hello everyone, my name is Kazuhiro Takahashi. I'm glad to be here at APAC Database Days today. I'm going to talk about a few consideration points of performance on Oracle 90C migration. Here's a brief introduction of myself. I'm a database specialist in Entity Data Corporation in Japan. I support integration projects for various large enterprise systems such as utilities, telecommunications, and governments in terms of database design, migration, and troubleshooting, specifically for Oracle and Exadata. I am Oracle Ace and working to contribute to Oracle communities such as Japan Oracle User Group and My Oracle Support Community. Here is the agenda of today's presentation. I'm going to talk about the following 4 points that are migrating to 90C optimizer, utilizing pending statistics, utilizing smart scan, and efficient test with PDB flashback. This presentation is based on a 19C migration project for a mission-critical system in which I dedicated as a leader of the database team from 2017 till 2021. Specifically, the system was migrating from on-premise 11G-R1 and 9IR2 to 19C Exadata consolidated. The project started with 12CR2 and we upgraded to 19C in 2019 spring. From this experience, I would like to talk about the 4 points that I think are better to consider in design phase, as well as some tips that are good to know in advance. First, I'm going to talk about optimizer migration. Since the applications on the database were very large, including more than 50,000 SQLs, it was impossible to test each SQL's performance in a given time. So it was important for us to determine new optimizers' behavior in design phase so as to reduce the amount of SQLs to be tuned in performance test phase. So here are the basic processes that we took for migrating optimizer to 19C. First, we determine a basic migration policy for new optimizer. Next, based on the policy, we design initialization parameters to control optimizer's behavior in detail. Third, we design operations of statistics gathering. Finally, we confirm the performance of applications and tune the slow SQLs if necessary. Actually, these processes were not always straightforward. Sometimes we had to go back and forth between processes. In the following slides, I'm going to describe how we did each process and share what we found in more detail. The first process is to determine the basic migration policy. In our project, there were two important requirements for database optimizer. One of the requirements was that we didn't want to change applications as possible as we could, and at the same time, we want all SQLs to be performant, meaning the same or similar execution plans as 11G. Of course, Oracle's optimizer has been improved over time, and there are good chances that 19C optimizer will come up with better execution plans for specific cases. However, in our case, there were so many SQLs that were running fine in the old system, and we expected the performance on the Exadata should meet the requirement if the execution plans are the same. The other requirement is stable performance. In another word, to minimize the risk of execution plan change on service time. So how those requirements will be implemented into the Oracle? What are the points to be considered? This figure shows a flow that Oracle changes an execution plan. There are basically two parts. One is hard parse and the other is statistics gathering. Oracle provides features to control the flow, such as hint, SPM, adaptive query optimization, adaptive statistics. For each feature, we decided whether to inherit, change, or utilize new feature as a basic policy in order to realize the requirements. For example, we decided to continue to use existing hints, logging some statistics, not to use SPM as it used to be. We decided to change manual to automatic statistics gathering. We decided to utilize new features such as pending stats, but disable adaptive feature. This is an example that how we determined not to use adaptive features, which basically change execution plans dynamically for better performance. Since we needed stable performance, for each feature we confirmed that they are not necessary considering the system characteristics. The second process is designing initialization parameters. As a top-down approach, we examined new and obsolete parameters from Oracle's manual. Specifically, it was important to configure parameters that relates to adaptive query optimization in terms of migrating from 11G. Also, mind that in 19C, online stats gathering on direct path load is enabled by default. Although it's a useful feature for data warehouse, it requires extra time to gather statistics, so we had to disable it. As a bottom-up approach, we examined actual configuration of parameters. Specifically, we took 53 trace and compare optimizers related parameters between 11G and 19C. It is very easy to take 53 trace, by the way, as it's shown here. In this case, SQL can be anything such as selecting a deal table. You will find initialization parameters in parameters used by the optimizer section, which you can use for comparison. For each difference, you can determine whether to inherit the configuration or not. If hidden parameters were changed explicitly in the old system, they should be carefully examined. In our case, some optimizers functionality were disabled as a workaround to avoid 11G's bug. We checked whether those bugs were already fixed in our 19C version, and if it's fixed, we basically left the value as default of 19C because hidden parameters should be modified by instructions from Oracle support. As a reference, this is a sample output of 53 trace in my test environment on VirtualBox. At the beginning part of the trace, there is the parameters used by the optimizer section, in which you can find all the initialization parameters that relates to optimizer's behavior. Just you can just copy and paste this section on Excel, and it will be easy to compare. You may notice that there are not so many parameters that need to pay attention to, because you can ignore parameters that depend on environment, such as database versions, the number of CPUs, and memory size. Also, parameters that appears only in the new version can be ignored as well in terms of a bottom-up approach. Although some people say optimizers parameters can be confirmed by VDR sys optimizers env, I recommend to use 53 trace for this purpose because it includes hidden parameters. This is the result of initialization parameters that we examined. The red letters show the value is changed from its default value. The configuration of parameters from number 1 to number 4 disables adaptive plan feature, and number 11 disables online stats gathering on direct pass load. From number 5 to number 8, we inherited our old system's configuration. I'm going to talk about the third process, design of statistics gathering operation. First of all, I would like to describe a whole picture before we go into the detail. As shown here, statistics information consists of three parts, namely object stats, dictionary and fixed stats, and system stats. The object stats are for tables and indexes. They exist both CDB and PDB level. The dictionary and fixed stats are for dictionary tables, and its base tables such as Exadata tables, which users are not usually aware of. The system stats are I/O and CPU performance-related statistics. They exist only in CDB. In addition to statistics information, there is an automatic statistics gathering feature. The feature can be controlled in CDB and PDB independently by maintenance task and AutoStats target preference. So how did we design? Oh, as you can see, as far as AutoStat is used, you don't basically have to worry about dictionary and fixed stats, as well as object stats in CDB level. So we didn't have to do anything about them. Regarding system stats, we made sure that the same statistics were used in all Exadata environments so that it can reproduce the same execution plan between different environments. Regarding object stats, we decided to introduce pending stats by setting publish table preference to true. We had some tables whose statistics were artificially set and locked for critical applications. We basically inherit all the system's policy for such tables. I would like to mention one more thing. In the performance test phase, we had to stop AutoStats gathering so as to avoid statistics are changed during the test. In this purpose, we switched AutoStats target from Auth to Oracle in PDB level. It was very useful because it can only stop gathering object stats in PDB, and other statistics can be corrected as usual. The last process is a performance test. For each performance issue, we identified the slow queries, analyzed the root cause, and came up with a realistic solution. Actually, in this process, we didn't experience a lot of slow queries. Instead, we had some issues relatively difficult to analyze as shown here. I don't have time to explain all in detail here, but from this experience, I'd like to let you know that we found 53 tries very useful for analyzing optimizers' behavior, specifically when we had to understand the reason of a different execution plan for a specific query between old and new version. In fact, concerning first and second issues shown here, it was easy to identify the execution plan was not good, but it was difficult why optimizer chose the bad plan. Even though it is difficult to read and understand 53 traces, I wouldn't imagine if we could reach to a better resolution without the trace. Another thing is that overall Oracle and Exadata knowledge was necessary for resolving such performance issues. For example, concerning the third issue, that we experienced a very slow full scan of a nightly DWH batch application, it would be difficult to understand the root cause if you don't know how to read hash and AWR as well as deep knowledge about Oracle and Exadata architecture, such as delayed block cleanout and Exadata's weakness regarding smart scans. Let's look at the 53 trace and see how an execution plan is determined. Here is a trace of estimating cost of two tables, depth and emp, with different join methods such as nested loop, sort merge, and hash join. By comparing each cost of join method, the optimizer decided the best join method will be hash join because it has the lowest cost. As a result, the final execution plan became like this: hash join of depth and emp table. In this slide, I would also like to explain Oracle's delayed block cleanout in more detail, as it relates to a later slide. Oracle writes blocks to a storage as uncommit state when a transaction cannot fit in the buffer cache. Oracle doesn't change the block upon the transaction commit. Instead, a select first accessing to the block will change the state by reading undo blocks. This is called delayed block cleanout. This figure explains what happened in the third issue in the performance test. First, a table is truncated and inserted by insert into select. Since the insert is conventional, it goes through the buffer cache. There are similar inserts running to different tables concurrently. The buffer cache becomes insufficient and the database writer has to write uncommit blocks from buffer cache to the storage. Several hours later, a select to the table experiences severe performance degradation because for each uncommit block, it needs to clean out the block. In that process, excessive single block reads to undo segment happens. In addition to that, Exadata cannot use smart scan in this situation. Huge performance degradation is observed. After the first select completed and cleanout finished, the same select runs just fine without any performance problem, which makes it difficult to troubleshoot the issue. I will explain such Exadata's characteristics in a later slide. I'm going to talk about the second point, utilizing pending statistics. First, let me explain the basic feature of pending stats. It is used to be that gathering statistics directly affects applications' execution plans, so gathering and publishing were always together. Now it's with pending stats, you can save statistics but not published immediately after gathering. Later on, the saved statistics can be published at any time. It's even possible to switch the optimizer to look at the saved statistics at session level and confirm execution plans by a command like explain plan for prior to actually publishing them. So it is a very useful feature to avoid performance degradation caused by gathering statistics. I'm going to explain how we utilize the pending statistics in this project. In the old system, in order to mitigate the risk of performance degradation caused by gathering statistics, there was a job running every morning that compares execution plans and see if they matches with already confirmed execution plans. If there's any difference, it notifies the operation managers by email, and system engineer will be called and assigned for further analysis immediately. so the operational burden was high. Upon the migration, we changed the job to use pending statistics. Specifically, we changed the job to check the execution plan against the saved pending statistics. Besides, we changed the frequency of the job every 2 weeks. Now, if any change is found, then it can be checked during next business day. And after the confirmation, the pending statistics are published. As a result, system engineers won't be called early in the morning anymore, and the operational burden is greatly reduced. Actually, we found two issues regarding pending statistics. Although they are not critical and have a workarounds, I'd like to just share the reference because I think it might be good to know in advance. The first issue is a performance problem of pending stats. The symptom is that gathering pending stats just takes long time when they are not published frequently. This issue is described as expected behavior in DocID as shown here, and it's recommended to publish pending stats frequently. Although we identified a slow delete statement that causes this problem, and we confirmed that a SQL hint can improve the issue, it is not recommended to do so in general. The second issue is a bug of gather table stats procedure with cascading option. The symptom is that after gathering pending stats on a table with cascading option, the num rows of the index becomes 0, even if the table contains more than one rows. This is a little bit complex issue to explain here, so it may be easier for you to take a look at a test case that reproduces the issue, which I posted on discussion in Mosque. Actually, this issue was filed as a new bug, and I confirmed it wasn't fixed until 1911. But I believe it will be fixed someday in the future. In the meantime, the check SQL shown here might be helpful. I'm going to talk about the third point, utilizing Smart Scan. Smart Scan is Exadata's functionality to speed up a full scan by offloading a part of its query operations to storage layer. Smart Scan is application transparent. That means no query modification necessary to use the functionality. In this project, there was a process in the migration application that involves a large amount of data loading and conversion from old database to new database. And SmartScan was actively used to meet performance requirements. From the experience with SmartScan, I'd like to talk about how to control it, specifically its prerequisites and blocking factors of SmartScan. First, I would like to explain the prerequisites. In order for SmartScan to happen, the query must meet the following three conditions. The query is executed on Exadata and the object must be stored on Exadata storage. And the query has to be a full scan of table, index, or partitions. And the query has to use direct path read. The first two conditions are easy to understand, but the last condition is a little bit difficult because the decision logic of direct path read depends on Oracle's versions and has not been published. I think some important points of DPL decisions are the following. DPL happens depending on the percentage of the segment size against the size of buffer cache. There are three thresholds, STT, MTT, VLOT, and if the percentage exceeds the STT threshold, DPL start to happen. The logic is different in serial and parallel query in terms of the threshold, and it's good to know that practically a parallel query always makes the DPL to happen. In order to understand this, I'd like to introduce NSMTIO trace, which I used to identify the DPL decision. NSMTIO trace is a way to identify the DPL decision. It is easy to turn on and off with auto session set events as shown here, and you will find a trace with NSMTIO something as shown here. If you carefully read the lines with NSMTIO and find a word direct read, that means the DPL is happening in the query. If not, it will appear as a word no direct read. If you look at QERTB fetch function just before the word direct read, you will find words such as MTT and VLOT. These are the thresholds, and you can understand that the object size is compared with the thresholds. As far as we tested in our environment of 19C Exadata X7.X72, the threshold of STT is 2% of the size of buffer cache, and MTT is 10%, and VLOT is 5 times of the size of buffer cache. In addition to the threshold, it is written that DPL decision can be affected by cost to read from local buffer cache or cache fusion, and compression state such as OLTP or Exadata hybrid columnar compression. As you can see, it is very complex to understand the logic, and I think the only effective way is to look at the trace for a specific query and see what is happening in your own environment. For a reference, this is a test result of the DPL decision in my test environment of 19.3 VirtualBox. I confirmed NSMTIO trace messages with different segment size around the threshold of STT, MTT, and VLOT. The vertical axis shows the segment size and threshold. There were two test cases, one for serial, the other for parallel. As you can see, serial direct pass read starts to happen from 2%, whereas parallel starts to happen even under 2%. That means it is possible to make a query to DPL with parallel hint. The result is only an example of a specific environment and test case, and numbers can vary in different versions, but at least I think it is good to know that you can identify the DPL decision like this figure with the NSMTIO trace. So far, I was talking about the prerequisites of Smart Scan. Here, I would like to talk about blocking factors. If there is a blocking factor, Smart Scan won't happen even if all the prerequisites are satisfied. We experienced two Smart Scan blocking factors that are delayed block cleanouts and table fragmentation, such as change rows, migrate rows. If there is such a blocking factor, typical symptom you may find is excessive single block reads wait events instead of Smart Scan. Specifically, you will find a lot of cell single block physical read in AWR, and in the case of delayed block cleanouts, undo segments are read. And in the case of fragmentation, table segments are red. This basically happens because SmartScan cannot complete offload operations in each storage server independently. For example, in the case of delayed block cleanouts, Oracle needs to change blocks from uncommitted state to committed state on buffer cache. In the case of fragmentation, chained and migrated rows are distributed more than one storage server and have to be loaded on buffer cache. In order for SmartScan to work, we must take away the blocking factors. This table summarizes the analysis methods and resolutions for each blocking factors. Basically, the point is to remove the blocking factor from the state of the table and make it suitable for SmartScan before the query is executed. First, let's look at the delayed block cleanout. The key points to determine are the single block reads to undo block occur and that they are not reproduced by reruns. There are several ways to deal with this, but the easiest way I think is to extend the buffer cache. It is also effective to use direct pass insert at load time to avoid the buffer cache. Next, we discuss fragmentation. This one is determined by the fact that single block reads to the table occur, and the table is fragmented. Although it is difficult to say, we should be suspicious if the fragmentation rate exceeds 10 to 20%. Reorganization is of course an effective remedy. However, it is also effective to use direct pass insert to prevent fragmentation in the first place. Especially for tables with more than 255 columns, it is better to use direct pass insert than conventional insert. For reference, here is a chart that summarizes Exadata's I/O statistics. It is based on the book Expert Oracle Exadata. The top is the DB server, and the bottom is the storage server, and the arrows represent the data flow. Here, when a full scan or consistent read is requested from the DB server, the rack cache fusion is checked, and if not found, I/O requests are sent to the storage server. The blocks read from the physical disks on each storage server go through the smart scan box and returns the offloaded results to the DB server. What I want to focus on here is the flow of the red arrow that returns the blocks directly to the DB server. I think this is where the blocking factors can cause single block reads. Although I'm not 100% sure if this is correct, I think it is possible to understand what is happening in the storage server by understanding the flow of I/O statistics. Now, I'm going to talk about the last point, efficient tests with PDB flashback. We believe it's important to consider how to maintain and operate the database in the test environment during the test phase. Since we had to create and maintain more than 100 databases, we thought that we could not keep up with the speed of the test phase if we had to do it manually. In this project, we focused on the database objects and their lifecycle, and we came up with a strategy for creating and restoring the test databases as shown in the table here. Specifically, we decided to take advantage of Oracle's backup and recovery and multi-tenant feature and we aimed to realize a flexible and agile testing environment. For, for example, we used PDB clone to distribute many PDBs as well as flashback DB to restore data. On top of that, what I'd like to emphasize here is the efficiency of DB restore. In the performance test, the efficiency of DB restore directly leads to higher test efficiency and application quality. Simple export-import takes time depending on the DB size. In order to complete the test scenario in a limited period of time, it is necessary to select the optimal DB restore method based on the environment and test data scale. The table here summarizes what backup and recovery methods are used in each environment. In a large-scale environment with several terabytes of data, a full RMAN restore would have taken about 3 hours. By using flashback DB, we were able to reduce this time to less than 30 minutes. One-time savings may not seem like much, but in reality, a restore can be performed many times during each test phase. In addition, by preparing a backup recovery shell and automatically running tests at night, we were able to complete all test scenarios in a given period of time. In total, we believe this contributed considerably to the efficiency of the testing process. Here is an explanation of flashback DB in comparison with RMAN. The advantage of flashback DB is its fast recovery. A full DB restore is not required. Also, creating the restore point is completed in a second. This is suitable when you want the database to roll back to a slightly previous state of data over and over again. A side effect would be additional I/O load for the flashback log and management of flashback area. The flashback area will need to be adjusted to the retention period and the amount of updates. If it overflows, the DB will stop, so it's important to design the disk group with a sufficient amount of space. Flashback DB's recovery time depends on the amount of updates. Since we do not update the entire DB in user tests, it is fast enough compared to RMAN recovery. We also found it was even useful for testing DDL releases. By the way, flashback DB restore points are not a substitute for RMAN backups. What if a restore point is incorrectly specified and the flashback DB fails? What if the flashback log has been deleted after the retention period has expired? There will be cases where the DB must be recovered from RMAN. I think it is recommended to use both in conjunction with each other. Here is an image of how flashbacks are used during actual testing. First, create a RMAN backup of the initial state of database. Next, create a restore point, run a test number 1, and flashback DB, and repeat the cycle. You can raise data as needed, then repeat the cycle for test number 2, and so on. When switching from one test phase to another, the data has to be recreated, and we are back at the beginning again. For example, switching data from performance test to operational test. One point to note at this time is that it is important to plan the test to avoid cross-incarnation recovery. As shown in the figure here, there are backups for performance tests and operational tests. Once the backup for the performance test is restored, the next time the backup for the operational test is restored, it will require cross-incarnation recovery. The recovery process is a bit difficult because it includes incarnation reset. Besides, the incarnation reset at the PDB level is not possible in 19C. It is recommended to avoid such cases when planning tests. By the way, in 21C, incarnation reset is available in PDB level, and we welcome this modest but definite improvement. As a summary, today I talked about optimizer migration, utilizing pending stats and smart scan, and efficient tests with PDB flashback as a consideration points of performance on 19C migration. I believe proper design will help reduce performance issues, but still, they won't be eliminated completely and require database experts who know about Oracle and Exadata architecture. A backup restore strategy for test environments is important to improve efficiency of performance tests and application quality. Flashback DB is one option to realize a flexible testing environment. As a final word, I would recommend you to consider how new Oracle features can be applied to solve the current operational problems in early design phase. Oracle has been continuously evolving, and there must be a lot of useful features available upon migration. I think the difficult part is to change the existing operations and people's mind, but I think strong passion will help to realize it. I hope this presentation will help migration projects to 19C by any means. Thank you.